Hey, thanks for joining us for this third video, I think, in the IR series. I forget how many, but the point of this video is going to be we're going to try to actually look at um, individual specific IR spectra, real life spectra, and see if we can make sense of them. And basically, when we say we make sense of them, we're going to assign each functional group or specifically each chemical bond to each band or peak that we see. And remember the breakdown, right? The big atom to small atom bands appear around here. So those are the hydrogen to nitrogen, oxygen, or carbon. Triple bonds appear over here. The double bonds appear over here. The single bonds between the big atoms or bigger atoms, bigger as in bigger than hydrogen, those appear in the fingerprint region that we're not going to worry about, at least for this, our class. Here's an alkane spectrum. Fairly simple because there's really not much of a functional group going on, right? This is N-octane. The main thing, really the only main thing I want you to get out of this is you see the three uh, bands that are a little bit close, pretty close to 3,000, but not quite 3,000, like between 2,800 and 3,000 wave numbers. That's the sp3ch stretch, right? So any compound that has any molecule that has a sp3ch will have bands in that area. And you can make something out of the fact that there's no bands here, right? That does tell us that this compound has no functional group. Remember, these are the sort of interesting, like a scissor and rock type of motion that we don't have to necessarily know about in the fingerprint region. Here's alkenes. Okay, we have the even in an alkene molecule, there's the alkane chain uh, on somewhere, so that we're gonna still see the sp3ch stretch right at 3,000. It's a really good idea for you to draw like a line at 3,000 wave numbers, because whether there's a peak immediately before or after means a lot in terms of diagnosis of what we have here. So if you have a peak at all after 3000, that's usually sp2ch, like this one. Now this band or peak is pretty prominent. Often it's pretty tiny, like this big. So just be aware of that. Of course, we see the carbon-carbon double bond stretch that is kind of right at the cutoff for the fingerprint region here. And actually, I'm not really sure what this band is, and sometimes you do see some unexplainable peaks in a real life spectrum just because there's sort of like the background noise stuff, right? So, what about triple bonds? Here's two different alkyne compounds. The top one is what we call terminal alkyne, because the alkyne or the triple bond is at the end of the chain. Whereas this, we might say that's an internal alkyne in the middle, and it looks quite different. I want you to notice when it's terminal, you have that unique sp carbon to hydrogen bond that has an even higher wave number than normal for like sp2ch stretch, so like way out here. Now this also, it's usually smaller than what this textbook has spectrum shows you. Again, we have the sp3ch because there's the sp3 part of the molecule, and then the triple bond stretch appears around 21 to 2200 wave numbers. Often this can be also pretty small, just so you know. Now, you might be puzzled to see this spectrum because you do have an alkyne, but you don't see the triple bond stretch, and the reason is this stretch is usually enhanced by some sort of polarity. So if there's no polarity in the triple bond, often you don't see the stretch at all. I want you to notice there is polarity here, because on this right side of this alkyne, this carbon is attached to another carbon, whereas this alkyne sp carbon is attached to a hydrogen. So there's quite a bit of electronegativity disparity between the left and the right, and that's why you see the stretch, but we don't have that in the symmetrical internal alkyne, so you don't see there. And of course, there's no CH stretch because there's no alkyne CH. So these internal alkynes are hard to spot from an IR. Okay. And what about these OH peaks, right? Those appear, remember, way downfield, or I should say high wave numbers, like 3300 wave numbers. Alcohol is very broad and very characteristic. NH is a little bit sharper, kind of like sp2ch and sp3ch. If you have primary amine, I want you to notice you have two hydrogens. It's a primary amine because the nitrogen is only attached to one carbon, so it's primary, but it has two sharp spikes because of the two hydrogens. If you have secondary amine, you only have one hydrogen, so you typically just one sharp peak. And here's what they look like. Here's alcohol. Again, the prominence of each of these bands could depend on the spectrum. You see that around 3300. The key idea is that it's broad for that OH. Okay. Again, you see sp3ch still. Here's secondary amine. Again, around the same wave number, but the size of the peak and the sort of the sharpness of the peak is quite different. And then we only see one spike because there's only one NH hydrogen. Now, I do want to show you kind of what sort of like more of a less textbook, real life spectra looks like. The top is sort of the textbook spectrum of the cyclohexene. I noticed the olefin there, right? But the other half, we have a bunch of sp3chs. So remember we said it's a good idea to draw a line at 3000. To the right, we have some bands. So that tells us that's aliphatic sp3. Aliphatic is kind of another little bit older word for alkane or alkyl group. So alkane CH or aliphatic CH is less than 3000, and then alkene or olefinic sp2ch stretches a little higher than 3000. And then we have peaks in the expected area for carbon-carbon double bond, and then of course we're going to ignore the fingerprint area. Now the bottom spectrum is something that one of my students, was it my student? Anyway, one of the students took OChem lab class, and if you compare it, right, like it's a little bit different, and it's good for you to be aware of these like real life difference. So what's the difference? Well, there's this peak around 2200. Why is that? Can you think of any reason why an sp carbon peak would sp carbon something peak would show up here? And that's because of CO2. If you draw out the structure of the central carbon is sp hybridized, so it shows up around here. And where do you think this came from? Because it's not in this molecule. If you guessed that the student was talking when they were acquiring the spectrum, you would be right. They were exhaling their CO2, and it's sensitive enough to pick that up. So if you do IR in the lab, remember just not to talk around the instrument. Okay, and then there's this broad peak, even though there's no alcohol in this molecule. This is likely due to water or moisture. Probably what the student did is one of the glassware pieces they were using, maybe they just washed it right before this acquisition, so it was still wet or something like that. Remember to always wash your glassware right after use. So it'll be dry by the time next time you need to use it. The carbon-carbon double bond area looks a little bit different. Again, even though the wave numbers are the same among these three peaks and these three, so don't base too much on what the appearance looks like, but look at more of the exact wave numbers because that's more trustworthy. Okay. Now, what about all the carbonyl peaks? Those are also very unique and diagnostic. And ketones, aldehydes, and carboxylic acids all show as peak around 1700, around 1710 wave numbers. Usually the strongest peak by far, so it's really easy to spot. Now, how do you tell the difference? Well, ketone is straightforward. Aldehyde has that unique CH stretch that shows up not in the regular sp2ch, but at around 2700 and 2800, you would have this twin peaks at those two wave numbers, roughly speaking. So you could tell aldehyde apart from ketone. Carboxylic acid would have that additional OH signal that's more than just the 1700, right? Usually centered around 3000, and it overlaps with a lot of things. Here's a ketone example. Of course, I want you to see the strong CO double bond stretch. Now, when you have a really, really strong signal like that, sometimes you get an artifact called overtone, which is right here. So I want you to note that that happens. Now, the way you can spot that is overtone, because of the physics involved that we're not going to get into. It shows up approximately twice the wave number of the strong peak. So here's 1700 super strong peak, or 1700 wave number. So the overtone should be around 3400, and indeed it is. And that's how you could kind of spot that that must not be a NH peak or something like that, but it's actually the overtone. Okay. Here's aldehyde example with the overtone again, but that strong signal for carbonyl, and then there's that sort of twin peak for the unique CH stretch of aldehyde that we were talking about. It shows up right there. Okay. So I want you to note those. Often, even though I said 2700 and 2800, often it's around 2020 and 2820. I mean 2720 and 2820. Here's a spectrum of a carboxylic acid. As before, there's still alkane part of the molecule that gives that normal, like a 2900 something CH stretch. I want you to notice how the OH stretch of carboxylic acid is centered around 3000 instead of like 3300 for the alcohol. So that's unique. And it tends to overlap with all these peaks, so that's kind of inconvenient because, well, overlap, and then you still see the carbonyl peak here. Okay, so you would, because both of these are present at the same time, you could diagnose it as a carboxylic acid. Now, one thing I want to point out when it comes to talking about these pi bond containing functional groups is conjugation lowers the IR frequency. Okay, what does that mean? Well, this is an isolated double bond, but here's a conjugated double bond, meaning two sp2 carbons of the two separate double bonds are next to each other. That means there's a p orbital here, p orbital here, p orbital here, p orbital here. They all have this pi overlap, and so for that reason, they're said to be conjugated. And because of all this extra pi overlap, they are even more stabilized. They're like kind of relaxed. It's kind of like when you have maybe friends next to you, you might be more relaxed than like strangers, bunch of strangers next to you, right? Kind of like that. So they vibrate at a lower frequency than isolated carbon-carbon double bond. And this gets even more intense for aromatic because it's all in resonance or conjugated. So even lower wave numbers. Now, you could say the same thing about carbonyl pi bonds as well. And if you see a really strong peak at like 1680 something, that often is an indication that you've got a carbonyl, but it's conjugated to another double bond, and therefore it's a lower wave number. So this wave number really is diagnostic. It tells you a lot. And of course, it's conjugation lowers and stabilizes because of extra resonance. And then you could say the same thing about ketones, aldehydes, and carboxylic acids. This is benzene with double bonds. And you could also say the same thing about amides. Back when we talked about resonance at the beginning of the semester, you might recall that amides have this resonance, right? And so for that reason, amide carbonyl also appears much lower than you expect. Here's an amide, primary amide spectrum. You see that strong peak around 1650-ish. I actually am not super sure why it's split into two bonds, or I mean two signals here. But there's also, you could see the two NH2 NH signals stretches out here. Again, there's two NH hydrogens, so you see two of them. Here's a nitrile that we haven't talked about yet, but that's a triple bond, right? So you see the triple bond peak around here. Often the nitrile band is much stronger than alkyne because it's much more polar. Okay. So that's kind of a summary of everything we just talked about, and in this diagram is a really good summary of everything we just discussed. In the class time and also in the future videos, we're going to be applying all that we just learned to doing things like molecular formula determination and whatnot. Okay, so we'll see you then.